Hello, once again I welcome you all to the lecture series of Mechanics of Solids. So in continuation with the previous discussion, today let's crack a problem using Macaulay's method. I hope you might have gone through the video of Macaulay's method derivation. Now we will apply the same methodology here to solve this question. When we talk about the question, let's say the simply supported beam has two loads, 48 kilonewton and 40 kilonewton, where the supports are at A and B and the loads are located at C and D. In this question, they have asked us to find out the deflection at C, deflection at D and Y max and its location. They have given that the Young's modulus is 2 into 10 power 5 megapascal and I as 85 into 10 power 6 mm raised to 4. So this is the data they have given, and using this data we have to solve this question using the Macaulay's method. Now, as I told in the previous session, we have to formulate an equation for the moment which consists of all the three sections AC, CD and DB. Now let us solve this problem by following the same procedure that we did in the previous lecture. That means, first of all, we will establish an equation for the section AC, then we will check the section equation that is developed for the section CD, and finally for DB. And after obtaining the last equation, we will check whether all the terms are included, or the sections or the terms corresponding to the sections are included in the final equation. Okay, now let's start. First, I am defining a section at between A and C. Okay, so I will define this section as XX and the length here is X. From A is X. If that is the case, then the moment at the section AC is given by RA into X. So here we have a reaction like this, and here we have a reaction like this, and for this particular question the value of reaction is 60 kilonewton and the reaction at B is 28 kilonewton. So altogether it will constitute 88 kilonewton, and this is the reaction. Now moment about AC, or the in between the section AC, can be represented as RA into X. Now let's move this section from AC to the section CD, where this length is defined as X. If that is the case, then the moment between C and D can be stated like RA into X, because this distance is X. Now we have to consider the moment due to the load 48. So minus 48 into X minus 1, because this length is going to be X minus 1. Now let's move the section from here to the last portion, that means in between D and C, whose distance from A is nothing but X. The 48 is located as at X minus 1 and 40 is located as X minus 3. If so, the moment in the section DB can be written as RA into X minus 48 into X minus 1 minus 40 into X minus 3. I think the dimensions are pretty clear, clearly noted in the question. Now if we look into the equation, we can say that the term for the moment AC is Ra into X, which is available there in the final equation. The moment equation for CD is Ra into X minus 48 into X minus 1. That is also available here. And finally section dB. That means we can say that if we choose this equation as a general equation, and if we take only the first term, that corresponds to section AC. If we consider the first two terms, it corresponds to section CD, and if we take all the terms, it corresponds to section dB. So right now we have obtained the equation for the B. This is the final equation. Now we have to equate it with the moment curvature relationship, where EI into d square y by dx square is equal to Ra into X minus 48 into X minus 1 minus 40 into X minus 3. So let's substitute the value. Ra is given as 60x minus 48 into X minus 1 minus 40 into X minus 3. Now we have to do the integration. So when you integrate once, we are going to get it as EI into d square y by dx. Sorry. It is going to be dy by dx is equal to 60 into x square by 2 plus c1. Now comes the block minus 48 into x minus 1 the whole square by 2. Because I am not expanding the brackets, I am simply considering that particular term as a single entity and integrate. So that is how you have to solve it when you use the Macaulay's method. That's how it is defined in Macaulay's method. That's the reason. Okay. Next, minus 40 into x minus 3 the whole square by 2. Now upon integrating one more time, the value is going to be EI into y is equal to 60 into x cube by 6 plus c1x plus c2. Now comes the block integrated separately, minus 48 into x minus 1 the whole cube by 6. Next block minus 40 by 6 into x minus 3 the whole cube. This is how the integration works. Now obviously you know what is the boundary. We have to substitute the boundary conditions to obtain the value of C1 and C2. Now what are the boundary conditions we are going to use? We are going to use the boundary condition 1, BC1, as at x is equal to 0, y is equal to 0. What is the second boundary condition? It is at x is equal to L. Sorry, it's not L. Right now we have a value with us. So it is going that x is equal to 6, y is equal to 0. 3 plus 2, 5 plus 1, 6. So at this location also displacement is 0. Here also displacement is 0. Right. So these two are the boundary conditions which we are supposed to substitute to find out the values of C1 and C2. So while substituting these boundary conditions, you have to consider the locations. That means if you substitute the first boundary condition, x is equal to 0, means it is coming at the location A, between A and C. Exactly at A, that means we have to consider the section AC. So let us do that. Okay. So while doing so, if we apply the first boundary condition, since it is located in the first section A and C, I will use only the first block. That means this particular block. So while doing that, EI into 0 equal to 10 into 0 plus C1 into 0 plus C2, which gives the value of C2 is equal to 0. Right. Now let's substitute this second boundary condition. So second boundary condition means at B. B means it is located in DB. That means you have to consider all the three blocks. That's how I explained the Macaulay's method. So when I substitute EI into 0 is equal to 10 into L is going to come as 6. So 6 cube plus C1 into 6 the block will appear. 48 by 6 is going to be 8 into L is going to be 6, right? 6 minus 1 the whole cube. Next the block will come minus 40 by 6 into L, sorry, always L is coming into picture, so 6 minus 3 the whole cube. This is how the equation is going to look like, right? So here we can say that the value of C1 is going to be obtained as 163.3. 163.3. A negative sign is also there. This is the value of C1, right? So when you, I don't know whether you have noticed it or not, we haven't converted the kilonewton into newtons, or we haven't converted the length meter into mm. We have substituted the value of load in kilonewtons and length in meters. That has to be there in your mind, because in the previous sessions I think majority of you might be solving the problem by taking the units as Newton and mm. Okay, so you should have a clear cut idea regarding the unit that you have substituted. Anyway, I will explain that when we find the deflection. When we substitute the values, we will have a discussion on that. Let's proceed. So when we rewrite this equation, how it is going to be? It is going to be like EI into Y is equal to 10 into x cube, 10x cube minus 163.33x, right? That's how the equation is, right? So if you look here, it is going to be 10 by 6 is 10, so 60 by 6 is 10, 10x cube plus C1x plus C2, right? So the equation is going to be, block is going to come minus 8 into x minus 1 the whole cube. Block is going to come 40 by 6 into x minus 3 the whole cube. So this is how the equation will look like, right? So let us put this system in brackets. Now what is the advantage of this equation? Because this equation can be used to find the deflection at any location. That means the total length of the beam is 6 meters. You can find out the deflection at 2 meter, 3 meter, 4 meter, 4.5 meter, 5 meter at any location. That means right now you have the freedom to find any value in between the section, in between the length, which was not available there in the double integration method. But obviously it can be obtained, but this is a more convenient form of solving a question in deflection. Now let us find the deflections at different locations. Now let us find the value at YC. That means that is at x is equal to 1, right? YC means at x is equal to 1, at x is equal to 3, right? So at x is equal to 1 means it is located in the first section, so you have to consider only the first term. If so, I will substitute it as EI into YC equal to 10x cube minus 163.33x. Now we have to substitute the values of E, I and x. But before you substitute, here you have to understand the dimensional homogeneity, or how the unit has to be substituted. Values has to be substituted, because we have the value of E as 2 into 10 power 5, right? We have the value of E as 2 into 10 power 5 Newton per mm square. We have the value of I as 85 into 10 power 6 mm raised to 4. That means if I want to substitute E and I in terms of Newton and mm, I have to make some necessary changes. And what are they? See, I told you that we have substituted the values of load in kilonewton, right? And length in meter. That means what will be the unit of 10x cube? It is going to be kilonewton meter cube, right? This is the unit right now they have, kilonewton meter cube. This is also kilonewton meter cube. So the left hand side unit and the right hand side unit has to be the same. So by making some necessary arrangements, like if I want to convert kilonewton meter cube to Newton meter cube, then things are in a same or on the same platform, on the same scale, we can substitute, right? So how will we do that? In order to convert kilo, I will multiply a 10 cube, right? So now it becomes Newton meter cube. Now we know that 1 meter is equal to 10 cube mm, right? So when we substitute it over here, I can say that 10 cube Newton into 10 cube the whole cube mm, right? So which is equal to into 10 power 3 into 10 power 9, altogether it is going to be into 10 power 12. That means to convert a kilonewton meter cube to Newton mm cube, I have to multiply a 10 power 12 on your right hand side. Right? This is how you have to solve it. So all these terms should be multiplied with a 10 power 12, right? Or else I will say I will solve it like this. So right now I am supposed to substitute the values, right? So let it be like this: EI into YC equal to 10 into, what is the value of x? It is 1 cube minus 163.33, and whose value is going to be obtained as minus 153.33, and this term has a unit of kilonewton meter cube. So in order to substitute everything in Newton and mm cube, I have to multiply a 10 power minus 12 here. So that means 153.33 into 10 power 12 will convert this into Newton mm cube. Since it is in Newton and mm, on your left hand side also you can substitute everything in terms of Newton and mm. So upon substituting, it is going to be 2 into 10 power 5 into 85 into 10 power 6 into YC, right? So this is going to give you the correct value. So the YC is going to be obtained as minus 9.09019 mm. So this is an area where you have to be very cautious. This area is an area where you should be very cautious. So majority of you might be busy with completing the procedure, and when you substitute, you might be in a hurry and you will directly substitute all these values and you are going to end up in trouble. So either you can convert these units initially, that means before starting the derivation, when I substitute here instead of 60, I could have substituted as 60 into 10 cube, right? Instead of this 1, I could have written it as 1000. Instead of this 3, I could have written it as 3000. If that is the way you are going to substitute, then there is no need to have a conversion like this towards the end. So while solving such kind of questions, have a clear-cut idea about the unit. Sometimes the loads will be directly given in units, in newtons. So please don't by heart, like always you have to multiply it with 10 to the power of 12. No, that's not the way to learn it. You have to understand what is the unit that is given in the question, and what is the what is the unit in which we are going to substitute the given data. A dimensional homogeneity should be maintained at every level of solution. Okay. Now, so we found the values of deflection at C. Now, if you want to find out the value of deflection at D, that means at x is equal to 3 meters. That means you have to take the first two terms, because it is going to include the section A, C and CD. So you have to consider the first two blocks, where EI into YD is equal to 10 into x cube minus 163.3 into x. Next term is 8 minus 8 into x minus 1 the whole cube. This is how it is going to look like. So you solve this You substitute x is equal to 3 meter, like 10 into 3 cube minus 163.3 into 3 minus 8 into 3 minus 1 the whole cube. So you are going to get the value as minus 283.9 into 9, right? And whose unit is kilo Newton meter cube. So which gives minus 283.9 into 10 power 12, going to give you the unit in Newton mm cube. Now you substitute the value of E and Y and obtain the relation for, so obtain the diffraction equation, right, at D. Now we have an interesting question here, which I have asked you to find, like a brainstorming question I have given in the previous session. I have asked you how we can find out the location of maximum diffraction. See, right now we have a beam like this, and you have a load here, you have another load here, and you have a section like this, right? So if that is the scenario, here you have got a 48, here you have a 40. So when we solve this, you should have an intuition where can be the location of the maximum diffraction, where can be. By looking at this itself, we can say that it is not going to come between A and C, because you have a 40 here, so it has to tend to that side. But it may not be between D and B, because a major load 48 is on the left hand side. So the intuition is something like the deflection, maximum deflection can be in between C and D. So that kind of intuition should be there. It's a bit tricky for some questions, but for this question it's very simple. That means it can be something like this. Here you have YC, but somewhere here you have a Y max. That means Y max is located somewhere between C and D. That means you have to consider the first two blocks. If that is the case, the general equation is EI into Y is equal to 10x cube minus 163.3x minus 8 into x minus 1 the whole cube, right? Now we have learned that at Y max dy by dx is equal to 0. So you differentiate this, what we are going to get? EI into dy by dx is equal to 10 into 3x square minus 163.3 is equal to, minus 8 into 3 into x minus 1 square, right? This is how you are going to differentiate. So this is going to be 30x square minus 163.3 minus 24 into x minus 1 the whole square, right? So upon expanding all these things and grouping, you are going to get the values as 6x square plus 48x minus 187.3 is equal to 0, and solve this equation gives the value of x equal to 2.87 meter, right? So here the length is 1 meter, here the length is 2 meter. That means somewhere between C and D, that means exactly at 2.87 meters from A, we have a maximum value of y. So this is going to be 2.87. Now things are very simple. You substitute the value of x is equal to 2.87 by considering the first two blocks. That's all. That is the end of the solution. So this is how you have to find out the value of location of maximum deflection and the value of maximum deflection. Okay, so kindly go through this solution part and try to solve one by one, so that you can have a better understanding. Only thing what I want to suggest is that be very careful when you solve this. Try to give your maximum concentration so that you don't make any kind of mistakes. And one more suggestion is that before you substitute any values into the equations, make sure that you are using the right units. Okay, that's my suggestion. So try to solve all these equations or all these problems. I will discuss one more question in Macaulay's method, and that's all for today's session. Bye bye. Thank you.